Hello and welcome to Module 4. My name is Andrew Otto, and the module today is on material selection, selection of surfacings, economic evaluation, and ancillary factors. The purpose of this module is to discuss key aspects that complete the pavement design process and that contribute to a successful pavement design. This will be in relation to the pavement design methods discussed in the guideline. And I urge you all to recall that the guideline is to be used in conjunction with country manuals. And thus this module gives an overview and not details of, for example, design of surfacings. Now, today's presentation is divided into 5 parts. The first part will be material selection. The second part will be selection of surfacings. Third part will be economic evaluation of pavement design options. And the fourth part will be ancillary factors and considerations. And finally, we'll conclude with a summary of what we will have discussed. Now, starting with material selection, significant research into the performance of low-volume roads in the last 2 decades has enabled us to gain a lot of knowledge on the use of appropriate materials for low-volume roads. This knowledge means we can now drop the use of terms such as marginal materials, non-standard materials, non-traditional materials, because these terms were used in relation to high-volume roads. We now refer to the materials as appropriate materials for low-volume roads. The extended research has also allowed the development of specifications for low-volume roads materials. It has also provided us with a greater understanding of the impact that drainage has on the performance of low-volume roads and the need to assess the impact of drainage on these materials. Now, the principles of selection of materials should be as follows. 1. Before selecting materials for use, you should always think of sustainability. That means use only the required quantity and quality of materials for your project without wasting material unnecessarily. The second principle that you should bear in mind is that the knowledge of performance of particular materials in particular areas and the local experience gained in use could override imported specifications. And the third principle to bear in mind is that often if your materials do not meet specifications, please consider mechanical modification with another natural material before considering chemical modification. And the fourth principle is that where possible, consider the effect that the material will have on the internal pavement drainage. And the fifth principle is that chemical modification should only be used if it can be shown to be economically justifiable. And lastly, you should be aware that gravel size and cobble size materials offer an option to use construction types such as macadam or Telford constructions, so they should not be unnecessarily discarded. Now, test methods. There are several test methods that are used in different countries. For example, countries use the AASHTO test method, others use ASTM, others the British standards, others TMH, which are now referred to as SANS, and in some cases they're also country-specific test methods. Now, these methods, even for the same test, will have minor variations in procedure. These minor variations in procedure can sometimes yield different results for the same material, and therefore you should not use or mix these test methods arbitrarily. Now, material characteristics can also sometimes change during extraction, stockpiling, batching, and compaction. An example of a material that changes in handling significantly is scoria, also sometimes known as cinder gravels. It therefore means that verification tests should be conducted at different stages and necessary adjustments made to maintain the quality used for design. We now consider how we can use materials that present certain predominant characteristics and how we can deal with these characteristics and use the material in road provision. The first one on our list is high plasticity materials. Now, high plasticity often presents or is often associated with clay content of the fine fraction of the material. And plasticity is often assessed by Atterberg limit tests and linear shrinkage tests. Now, the problems which high plasticity materials can present is high absorption of moisture. And with the high absorption comes weakening of the material and swelling, which causes deformations on the pavement. Now, when these materials lose the moisture, they shrink and crack, and the cracking allows more moisture into the pavement. So it becomes a cycle. Now, this does not mean that high plasticity materials cannot be used. They can be used if you take care of them by providing what we have always been talking about, that is adequate drainage in the form of crown height, an adequate crown height, adequate invert depth, and use of sealed shoulders. Coupled with that is the need to carry out timely reseals in order to correct any cracking which may have started happening on the surfacing. And of course, in some cases, you may have to treat the material with lime or cement. Now, the next category of material that we shall discuss are poorly graded materials. Now, grading of materials is assessed mostly using particle size distribution tests. And poorly graded materials can present a variety of problems depending on the grading. For example, coarse graded materials will often result in poor stability in the pavement. And if used in the upper pavement layer or the base course, it can often result in potholing, a high binder demand to fill in voids, a poor surface finish, and for fine materials, they can often present problems of low shear strength, especially again when used in the upper pavement layers, They also have a potential for allowing capillary rise to manifest in the pavement structure. And for gap-graded materials, they are often difficult to compact, and with that comes poor stability. And because of the gap in the materials, fines can migrate from lower pavement layers and contaminate upper pavement layers, thus altering the properties of the upper pavement layers, often resulting in a loss of strength. Now, you can still use poorly graded materials provided that you address the grading by, for example, mechanical stabilization with other materials, or lime or cement modification to deal with effects of excess fines. Or during construction, you can actually, by use of labor, manually remove any oversized materials in case of very coarse materials. Or as a last resort, you may consider crushing of any oversized materials. Now, the next category of materials are those that are poorly shaped, or those with particles that are poorly shaped. Now, this is manifested through either rounded particles, flaky particles, or elongated particles. And they are usually assessed by visual inspection for rounded particles and flakiness and elongation tests. Now, materials with poorly shaped particles can present a variety of problems. For example, rounded materials offer poor stability and are also very difficult to compact. It's almost like trying to compact ball bearings. Flaky or elongated materials often end up breaking down under traffic or crashing during compaction, and some of them even rebound when they're compacted. An example of that are materials rich in mica. Now, poorly shaped materials can be used in pavements provided that you either crush the materials if the particles are rounded, or you carry out mechanical modification with other materials, or in the case of flakiness or elongation, this may require a slightly more expensive approach by either modifying crushing processes and changing or altering the setting of crusher plants to high impact crushing. The other type of materials that you need to consider are materials with low particle strength. And low particle strength is often caused by inherent defects in the fabric of the material, such as foliation. Now, they can also be caused by incomplete or weak in duration for pedogenic materials, or by weathering in situ. Now, particle strength is assessed by a variety of tests, common ones being the 10% fines aggregate crushing test, the aggregate impact value test, and the aggregate crushing value test. Low particle strength materials can present a variety of problems. They can break down under traffic or under compaction. They often result in reduced strength when compacted, and the particles that break down can often generate fines that are pumped into the upper layers of the pavement. But they also offer some advantages in that they are easily extracted, they are easily compacted, and sometimes their grading improves upon compaction. Therefore, if we are to use these in pavement layers, we have to address the characteristic by carefully screening the material during extraction to make sure you have slightly bigger particles so that when they are compacted, they break down to the correct size. You can also mechanically stabilize the material, and as a last resort, you can carry out lime or cement modification to give it more bulk strength. Now, another category of materials are those that have low durability. Now, durability is defined as the ability to maintain mechanical or chemical integrity over the design life of a road. And durability is assessed using also a variety of tests, such as the Los Angeles abrasion test, the sodium and magnesium soundness test, and the durability mill test or the Texas ball mill test. Low durability materials can cause a number of problems, such as degradation in service and subsequent loss in strength and stability. And once that occurs, then you expect cracking or rutting to occur with all its associated functionality problems. Again, this can be addressed by material screening, mechanical stabilization, and lime or cement modification. Now, I would like to share with you an approach that has recently come out in Australia, and it's discussed in detail in the publication presented on the slide here, Austros 2020. It's can be downloaded freely, so I encourage you to download and read through it. And this publication offers a risk-based approach to material selection for sealed roads. The method uses a matrix system, and the matrix has got traffic on one side measured in measure and the probability of mean annual rainfall exceeding 500 millimeters per year on the y-axis. Now, it's a 3x3 matrix, meaning that there are 3 traffic classes and 3 risk levels of rainfall exceeding 500 millimeters. And therefore, you will end up with 9 cells into which your rainfall fits and your traffic also fits. So depending on which cell your design conditions fall in, materials and their risk levels are then provided so that you're aware of the level of risk involved with using materials of certain characteristics. And the 3 key characteristics that are presented for the different materials in this case are the fineness ratio, the grading modulus, and the shrinkage product. Now, let us look at material specifications. For all the pavement design methods discussed, material selection, as discussed in the previous slides, should be used. That means you should pay consideration to the predominant characteristics that are described. Now, For CBR-based methods and also for the DCP-CBR method, specifications are often given in terms of strength, and strength is measured in CBR in this case. Particle size distribution envelopes, you may find up to 5 envelopes of which you have to choose from or comply to. Other times, the particle size is measured in terms of the grading modulus or specified in terms of grading modulus. Plasticity is specified in terms of plasticity index, plasticity modulus, linear shrinkage, or plasticity product. For the DCP-DN method, strength is specified in terms of the DN value, and particle size distribution is specified in terms of grading modulus. Plasticity, though measured, does not have a specification in this method. Now, material specifications for empirical pavement design methods take on a very simple form, in that these methods, such as the Telford and macadam type constructions, often only specify particle size distribution or dimensions of particles that must be used. And they occasionally also specify the crushing strength of samples of the material. And this goes as well for rigid pavement options such as concrete. Now, the methods, because of their empirical nature, or pure empirical nature, often give elaborate construction instructions. So the specifications are very simplistic, as you can see. Now, for gravel roads, the focus of material specifications is on the wearing course. And the wearing course also acts in most cases as the structural layer. Now, the aim of selecting or specifying materials for gravel roads is to minimize gravel loss and roughness. And we have provided layer thicknesses for different design traffic levels up to 0.3 meter in Chapter 6 of the RRN. There are also additional specifications to make sure that gravel loss and roughness are minimized, and also that the material should be able to withstand some amount of traffic. And these are in terms of strength measured as CBRs, particle size distribution envelopes, grading modulus or grading coefficient. Plasticity is specified in terms of plasticity product or shrinkage product. Once again, the Ostrods publication provides also a risk-based approach to the selection of wearing course materials in terms of grading modulus and shrinkage product. Here is an example of a chart to help in the selection of wearing course materials for gravel roads. Now, you may not have the luxury of having different materials to select from, but the chart in that case will show you what performance to expect from the different materials that you have. Bear in mind that these charts may need to be calibrated for local conditions of rainfall and for the volumes of heavy trucks that use the roads. Another presentation of a similar chart here uses the shrinkage product and the grading coefficient. And once again, These charts all need some calibration for local rainfall conditions and track traffic